Hi, it's Mr. Yeager, continuing with the optics unit. Now that we have practiced, we've gone through all of the mirror drawings and shown how we can describe the images based on the drawings. Now we got to go back and look at how we can describe the images based on the equations. So we need to obviously introduce the two equations. And so there are two equations that will be used for optics. These are the same equations used for mirrors and lenses. So there's only these two equations that you're going to be using during this particular unit. So you can see at the top one here I have the lens mirror formula. And you can see it's 1 over f equals 1 over the object distance plus 1 over the image distance. All right. So basically the reciprocal of the focal length, this is again the focal length, all right, is equal to the reciprocal of 1 over do plus 1 over di. All right. Now, I will show you in a minute how you can obviously change that to make it much easier for you to maybe understand. But understand, this is the way the equation is introduced in textbooks for optics. All right. It's an inverse formula, just like the resistance formula was in the electricity unit. Magnification. Magnification, denoted as M, is equal to the opposite of whatever the image distance is. So we have that negative sign on the outside because whatever the image distance is, you're going to basically do the opposite. So if it's positive, it's going to be negative. If it's negative, it's going to be positive. Divided by the object distance will equal, there's another part of this, the image height over the object height. There are no units for magnification because you can see we're dividing in most of these problems, centimeters over centimeters, centimeters over centimeters. All right. So distance is measured in centimeters. Height is going to be measured in centimeters. That'll be the most common unit, centimeters. Okay. For do, f, di, hi, and ho. Okay. All of them will be in centimeters generally. All right. So these are the formulas now that you have. Okay. If I take you back real fast, we went over this in a couple videos ago. If the image distance is positive, that means we have a real image. If it's negative, virtual image. If it's positive magnification, upright, negative magnification, inverted. If the absolute value, I say absolute value, again, I try to make you only focus on the number. If the number is greater than 1, the magnification number, it'll be an enlarged image, less than 1, diminished. If it's equal to 1, that means it's going to be the same size. All right? So that's something we covered. So you can see, we will be doing drawings and math, and they should both support each other. When students start doing this, some of them, they do all the math first, and then they go back and do the drawing to match it, basically. All right? Or some people like to do the drawing and then they go back to the math, hopefully having it confirm their drawing. Right? So it doesn't matter really which way you go. So we have a few problems we're going to work on together. All right? This is how your assignment's going to be, as well as your test in terms of these questions. So you have a 5-centimeter object placed 15 centimeters in front of a concave mirror with a focal point of 10 centimeters. Find di, m, hi, and describe. The only other thing I'm not going to do during this video is you would also have to draw a ray diagram of this. All right, so how do I figure this out? This 5 centimeters is referring to the object height. So this object is 5 centimeters tall. All right, and object, when we draw, again, always upright. All right, it's placed 15 centimeters in front of a concave mirror. Now, during the problem, we would definitely want to underline concave mirror so I could do the right type of drawing. But again, for this one, I only want to do the math. The object distance is 15 centimeters. And it says it has a focal point of 10 centimeters. All right? Find di, m, and hi. Now, I'll go ahead and I want to point this out real fast. When you do the ray diagram, you would have to understand where is this object? And maybe, again, if you really know what happens when the object's placed in certain places, you should already basically anticipate what the answers should look like, the mathematical answers. The focal length is 10 centimeters. What's the other point we need to make sure we have? The principal axis. The principal axis is always double that. My object is at 15 centimeters, so my object is between C and F. Now you can go back to the old video, you can go back to your old notes and go, well, now I already know how to describe it. And that's fine. You could totally do that. Okay? But in this video, we're trying to show how the math will describe it the same way that we did it in the drawings. All right? So we have these numbers. All right? HO 5 centimeters, DO 15 centimeters, and F 10 centimeters. All right. So let's find DI. All right. So my formula would be 1 over F equals 1 over DO plus 1 over DI. Now, I don't want to stop you. If you absolutely feel comfortable and I have no problem with it, you can definitely plug this in as 1 over 10 equals 1 over 15 plus 1 over DI and try to solve. That is fine. There is zero problem with that. And I mean, as long as you do it correctly and obviously take the inverse of your final answer. So there's nothing wrong with that. The thing is, we often like to rearrange this to make a little bit more sense out of it and get an answer immediately. I want to basically inverse everything. And I can't just flip it over. That's not not allowed. But again, if you want to solve for it this way, do it. Do it, do it, do it. I want to show you how we basically adjust the formula. All right? So, basically, I have F and DO. I want to solve for DI. So I'm going to move DO to the other side. So 1 over DI will equal 1 over F minus 1 over DO. What we can then do is I want to create a common denominator. So how do I do that? I basically cross multiply. I put DO on top of F, and I put F on top of DO, and I make a common denominator now. Now it's going to be DO over F. So I have 1 over DI equals DO over DOF minus F over DOF. All right. Basically, this is just a mathematical trick that probably a lot of you guys already know. All right. So now I can combine the two numerator components because I have the same denominator. So 1 over DI equals DO minus F over DOF. Now that I only have one fraction on both sides, now I can inverse it. And DI will equal DOF over DO minus F. All right? And some students are able just to memorize that. And that's, again, another way we do this. This is something that I have memorized just because I understand where it came from, and obviously I've used it a lot. Hopefully, if you keep on using it, you'll remember the formula too. This is how you will be given the formula on the test up here. But if you know how to change it, do it. A lot of times people see it's D before F and then D minus F. It's multiply and then subtract with D always first. So now if I solve this problem, okay, I'm going to erase a little bit here. I can find the DI. DI will equal 15 times 10 over 15 minus 10. Okay, 15 times 10 over 15 minus 10, that's 150 over 5. And that will equal, what's that, 30? Yep, 30 centimeters. It'll be at 30 centimeters. So my image distance will be at 30 centimeters. So hold that in the back of your mind. Let's find the magnification now. Magnification equals negative DI over DO. So that will equal negative 30 over DO is 15. My magnification is negative 2. Negative 2. Now, so I have now my image distance and my magnification, negative 2. Let me find my image height. So magnification equals image height over object height. So negative 2 equals HI over object height, 5. 5 times negative 2, HI will be negative 10 centimeters. Negative 10 centimeters. All right? So, this is all stuff that we basically expected if you go back and look at your chart for all of the situation when you are between C and F, when you place the object between C and F. Look at it. What type of DI do I have? I have a positive DI, which means my image will be real. It'll be in front of the mirror. I have a negative magnification, which means my image is inverted. But my magnification is greater than 1. 2 is greater than 1, so my image will be enlarged. And then the last thing to figure out really is, where is it? Where is the image? Well, this is why it's important to know you have your focal point is at 10 centimeters, your principal axis is at 20, you're at 30, so you are beyond C, or image distance is greater than C. That would be fine. And that's what we would have expected. When we are between C and F, when we put those two lines together, this is not going to be completely accurate because I didn't measure it, scale anything. We should be beyond C. That wasn't, like I said, not scaled. That image is produced beyond C. It is inverted. It should be enlarged. Again, this is not the scale, kind of roughly done. All right. So it should support your answer. Again, why you can do math or the drawing to help you get the answer. So let's do a second one real quick. This one's going to go a lot faster. I have my object height. I have my object distance. And I have a convex mirror. This is something I would underline for my drawing. And the focal point is -5 centimeters. All right, that makes sense. For a convex mirror, the focal point is on the opposite side of the mirror, on the negative distance side, so it's negative. So if I go ahead and solve for everything I want to solve for here, again, like I said, I'm going to do this a lot faster this time. di is equal to dof over do minus f. Again, you can use the reciprocals. There's zero problem with that. You will get 10 times -5 divided by 10 minus -5. Please do your math right. This is add the negative. So I get -50 over 15, and that would be -3.3 centimeters. -3.3 centimeters. Okay? Yeah, that's it. -3.3 centimeters. Okay? So we get -3.3 centimeters. I'm trying to think about this real fast for a second. I feel like something. Oh, everything's right there. Okay. -3.3 centimeters. All right. So let's go ahead and set this up. All right, sorry about that. So we get -3.3 centimeters. All right. So now I can find my magnification. My magnification is going to be -3.3 di over do 10. And so my magnification is 0.33, positive. I get rid of the negative sign. So my magnification is 0.33. And therefore, if I find my object or my image height, 0.33 will equal image height over object height times 3. 3 times 0.33, my image height will be 1 centimeter. 1 centimeter. So what does this mean about my image? I have a negative distance. That's a virtual image. All right. I have a positive magnification, which means that is upright. All right. But it's less than 1, so it's a diminished upright image. The height obviously supports this too. I have a positive height, which means it's going to be upright as well. And then where is my image? Well, if it's virtual, it's on the opposite side. I would just say the object is at -di. Remember, we just say that. Okay? So one more. Oh, one more. Really, I'm just doing this just because it might be given in just a different way. You have a 4 centimeter object. That's your HI. Not your HI. Your HO is placed 20 centimeters in front of a concave mirror, underlying concave mirror, with a principal axis. Ooh, there's the difference. That's why I'm doing this problem, of 20 centimeters. So I'm giving you C is 20 centimeters. So how do you figure out F? F is half of C. So my focal point is at 10 centimeters. My focal point is at 10 centimeters. But something for you to notice. The object is on the principal axis. So think about what should happen here. So my image, DOF over DO minus F, will equal 20 times 10 over 20 minus 10. So that's 200 over 10 is, hey, look at that. It's at 20 centimeters. That's what I'm expecting. It should be on the same spot. All right. My magnification, negative di over do. All right, well, it's negative 20 over 20. So, hey, my magnification is negative 1. That will then equal my image height over my object height. My object height is 4 centimeters. 4 times negative 1, hi equals negative 4 centimeters. This all supports what we're expecting. The image is real, positive di. It is on C. The image and object are on the same spot. The image is inverted, negative di, negative height. And it is the same size. It is 1. Magnification equals 1. All right? So that is what you do with the math. I'm not going to do a separate one for lens formulas because guess what? It's the exact same stuff. That's the nice thing is we do it once for this, you should be able to do it for lenses as well. All right? So that is it. Thank you.